Welcome back to another video. In this video, we'll cover how we measure the goodness of fit of a multinomial logit model. We'll also cover a canonical or foundational application of the methods we've talked about to a transportation expansion policy in San Francisco from nearly 50 years ago. Let's start by talking about some of the goodness of fit, and I'll pull up some slides here. So typically in a regression model, you would measure the goodness of fit by computing the R-squared. But in a discrete choice model, we don't have a continuous outcome variable to be able to measure things like the mean squared error. So in a logit model, we're going to use something called the likelihood ratio index, or more colloquially, McFadden's pseudo R-squared. And the formula for this is just the ratio of the fully estimated model, the likelihood function associated with that, compared to the log likelihood value of a model with only a constant term. And then we're going to take that ratio and subtract it from 1. So the range of this rho parameter, which is the pseudo R-squared, it's 0 if the model has 0 predictive power, and it's 1 if the model has perfect predictive power. However, unlike the R-squared from a regression model, there's not really an intuitive interpretation if you're moving among values between 0 and 1. The only real interpretation is at the endpoints of 0 and 1. This is why we call it a pseudo R-squared. You can think of this rho parameter as measuring the percentage increase in the log likelihood value above the model that has 0 parameters. But that's not super helpful for actually applying this to the real world. And some provisions that we need to keep in mind as we're thinking about what the rho parameter is. If we want to compare across models what the value of rho is, we need to use the same data set, have the same choice alternatives, and have the same baseline likelihood value. If we think about what the values of rho might be on the interior, well, we know that if rho is higher, then the fit is better, but we don't really know how much in the same way that we would with a linear R-squared. However, McFadden is on the record saying that values of 0.2 to 0.4 represent excellent fit. Let's talk about another common metric that is used that doesn't help us as much as the McFadden pseudo R-squared, and that is accuracy, or percentage correctly predicted. So this is a commonly reported metric in machine learning prediction, and basically what this is going to do is it's going to use predicted individual level choice probabilities and then assign whichever choice probability was the maximum, we're going to assign the person to have chosen that alternative. So the problems with this metric are that it contradicts the meaning of choice probabilities. If you remember back from the first video in this series, I talked about how we should think of epsilon as being a repeated draw from some distribution. And so if you thought about, well, how many times out of 100 would I choose to go to the Thai restaurant versus the Mexican restaurant? That's the correct meaning of the choice probability. It's a repeated draw from the unobservable preference distribution. So this construction of accuracy, as it's used in machine learning and such, it contradicts that meaning because it treats the probability as being known and the same no matter what. It's also dependent on an arbitrary threshold choice. So typically in like a binomial logit situation, we would say, well, if the predicted probability is over 0.5, then we're going to predict that 1 was chosen. Otherwise, we're going to predict that 0 was chosen. And this metric is also going to perform poorly with imbalanced choice sets. What we mean by imbalanced choice set is one of the options has a very small share, whereas the other option has a very large share. So this is common in like measuring disease prevalence, where maybe only 1 in 100 people have this particular disease, but we need to diagnose for it. That would be an example of an imbalanced choice set. So as I mentioned before, the choice probabilities are expected shares across multiple repetitions, not individual predictions. And this is going to give inaccurate market shares, and it implies perfect information. So don't use the percent correctly predicted. Do use the McFadden pseudo R-squared or the likelihood ratio index. So now that we have the ideas that we've covered in this mini-series, let's actually see how they're put into practice, or how they were put into practice during the pioneering times of discrete choice model development, which was in the 1970s. This was around the time that San Francisco was expanding its train service called Bay Area Rapid Transit, or BART. And Daniel McFadden was given the opportunity to analyze consumer choice of this new transit system. And he thought that these discrete choice methods would be superior to the existing methods at the time used by transportation researchers. So there's a little bit of a horse race aspect to this paper. So they surveyed 771 people who were just commuters in San Francisco. They didn't have to use public transit, but they could. And then they wanted to predict how the consumer choices would change when the new rail service became available. And they actually came up with a model that fit the data very well and performed very well in its counterfactual prediction. So let's kind of look at what that was, and I'll pull up the train. This is in the end of chapter 3 of the train textbook. So here's the summary of variables that were used in the choice model. There's not like a formal likelihood function included in the textbook. We could probably find that in the paper that was originally published. And this table is a little bit more difficult to read than what you would find in most scientific publications these days. It has numbers after the variables for which specifications they were included in. So this just means that the cost was included in all specifications, but then some of these things were included in different specifications. So I don't want to go through all of these exact point estimates. What I will say is that they got a likelihood ratio index of 0.4426, which is above that 0.2 to 0.4 range that McFadden said was an excellent fit. And I think the other interesting thing that is worth noting in this paper is that they have the cost of the commute in monetary terms. So like how much would it cost to gas up my car or to pay the toll across the bridge if I'm driving? How much would it cost to ride the train? How much would it cost to ride the bus? If I walk, it's free. But then they also have time costs as well. So if I walk, it's going to take longer. So that is a different form of cost. And then they can infer the value of time saved as a percentage of the wages that the person earns and see how that varies across the different modes of transport. So that's pretty interesting. And what they end up finding, so they end up using the model to make predictions for after BART opened. And their model predicted these shares. And then after BART opened, they got these shares. So basically, everything was very similar, except there was a little bit of an over-prediction of taking the bus, as well as a little bit over-prediction of the actual bus usage. So this is interesting. Obviously, like we talked about with the IIA assumption, they were using a logit model that had the limitations of the IIA. At the time they were doing this, the multinomial logit was the state of the art, and so there wasn't a known remedy for resolving the IIA limitations. But in part because of this research, that those new tools were developed, and now they're widely used today. So the BART study showed that these discrete choice methods are worth their salt and can be useful for making meaningful policy predictions. And for that reason, they passed the validation test, and now they're used quite frequently in almost every domain of empirical economics today. This wraps up this mini-series of videos. In the next mini-series, we'll talk about how we can generalize this logit model to come up with a framework that can make more reliable predictions in terms of substituting across different options and introducing more realistic choice behavior in other ways. So I hope you'll join me for the next one, and thanks for watching this one.